All right, guys, let's talk about that chapter 19 homework. So going into MyLab, again, I'll remind you, make sure you click these links over here to get all of your credit for the homework. But let's look right at the questions. Question 1. So we want to come up with the null and alternative hypotheses we would use to test each of the situations. All right. A mayor is concerned about his negatives, that is the percentage of city residents who express disapproval of his job performance. His political committee pays for a series of TV ads, hoping they can keep the negatives below 71%. They will use a follow-up polling to assess its ads effectiveness. Let P be the proportion of city residents who express disapproval of the mayor's hypothesis, mayor's performance, sorry. Okay, so notice that what we're trying to do here is we're trying to keep the negatives below 71%. So our null hypothesis is that it is 71 or above. Well, we should be able to do equals 71. And then we want to go below 71. It may require this one to be above. Let's check in a minute. All right, there we go. Is a four-sided die fair? Let P represent the probability of the die landing on any particular side. Okay, so we're looking to check to see if the die we roll is coming up with equal probability on each side, right? So the proportion on each side should equal 1/4. If it is not fair, it might come up greater than 1/4 or less than 1/4 since it's a four-sided die. I don't know which, so I'm going to go with it does not equal. Only about 24% of people who try to quit smoking succeed. Sellers of a motivational tape claim that listening to the recorded messages can help people succeed. All right, so we know about 24% succeed. We are hoping that the motivational tape will increase from 24%. After the political ad campaign, pollsters check the president's positives. They test the hypotheses that the ads produced no change against the alternative, that the positives are now above 59%, and find a p-value of 0.132. Which conclusion is appropriate? All right, there's a 13.2% chance that the natural sampling variation could produce poll results at least as far above 59% as these if there's really no change in public opinion. Okay, all right, if we look at this, the 86.8% chance that the ads worked, the chance that the ads didn't work, that's not what we're testing. We're testing to see whether the hypothesis produced a change in the political campaign, right? Or whether the people's opinion of the president's positives changed, right? So we're not looking at a chance that the poll we conducted is correct. That p-value represents the probability of ending up with a result as weird as ours by natural sampling variation alone if the null hypothesis is true. And my null hypothesis is really that there's, that 59%. So it's option A that's describing what's going on with that probability value. The seller of the loaded die claims that it will favor the outcome 6. We do not believe that claim and roll the die 200 times to test an appropriate hypothesis. Our p-value turns out to be 0.03. Which conclusion is appropriate? So this 0.03 is saying we'd get the result we got, or weirder, 3% of the time due to natural sampling variation alone. So it's not that the die is fair. There's a 3% chance that a loaded die could randomly produce the results we observed. No, there's a 3% chance that a fair die could randomly produce the results we observed. So it is reasonable to conclude the die is loaded. So we want to choose statement D is correct because it uses the p-value to describe the probability that the Well, let me see what my next choice. Okay, that the null hypothesis. No, wait. Alternative hypothesis. I've got to read the whole thing. Is no. I wish I could see these both at the same time so I could read them. Probability that the sample data, I have to go through everyone, is observed assuming the null hypothesis is true. My goodness, didn't that take some reasoning out? These drop-down menus can be painful, okay? But you just got to keep going until you find the right combination there, right? But the point is, the p-value represents the probability of getting a sample as weird or weirder than ours if the null hypothesis is true. A company's old analgesic formula provided relief for 52% of the people who used it. The company tests a new formula to see if it is better and gets a p-value of 0.433. Is it reasonable to conclude that the new formula and the old one are equally effective? Well, no, it's reasonable to conclude that this new one's not more effective, right? So since the p-value is greater than 0.05, it seems the new formula is more effective. No, that's not true. It would be if the p-value were less than 0.05, then the new formula would be more effective. It is not reasonable to conclude that the new formula and the old one are equally effective. The p-value cannot suggest a conclusion. That's true. It is not reasonable to conclude that the new formula and the old one are equally effective. There is a 43.3% chance the new formula is better than the old one. This statement is false. That's not what the p-value is telling you. The p-value is telling you if this really is the effective rate, the probability we would get a sample as weird as ours or weirder is 43.3%. That's pretty likely to happen, right? That's almost half the time that's going to happen. Since the p-value is greater than 0.05, it seems the new formula is equally as effective as the old one. No, that's not quite correct. Just because well, yeah, since the p-value is greater than 0.05, it seems that the new formula is equally as effective as the old one. We were testing here a one-sided hypothesis. We were testing to see if ours is better. The new formula is better than the old formula. So we can't get a conclusion with that p-value. But you got to be careful with the directional hypotheses, right? If I were, I really need a significance of a p-value that is significant for me to reach a conclusion, right? If this p-value had been less than 0.05, that would be pretty convincing evidence that the new formula is now more effective, all right? But when I've got a p-value that's large, it really doesn't tell me much because that could have just happened. A friend of yours claims to be psychic and you are skeptical. To test this, you take a stack of 100 playing cards and have your friend try to identify the suits. State the null hypothesis. Okay. My null hypothesis is that, wait, there we go. The friend's chance of guessing the correct suit is equal to 1/4 because there are 4 suits. So equal probability he could guess any one of the 4, right? To state the alternative hypothesis. If he's psychic, he should do it better than 1/4. So the friend's chance of guessing the correct suit is more than 1/4. If the p-value is 0.277, then there is not sufficient evidence to conclude that the friend can correctly identify more than 25% of the cards. Because this is bigger than what we would consider, so this is basically saying he'd get that result just by random sampling, by chance, 27% of the time. That's frequent enough that we wouldn't think he has a talent. If the p-value is 0.016, and notice this is saying he would now get that result as weird as his or weirder, right? He'd get that correct number of correct suits. By random sampling alone, just 1.6% of the time. That's a really rare occurrence. So it is sufficient evidence to conclude that he can correctly identify more than 25% of the cards, because there's a really small probability that he's just doing it by chance. In a rural area, only about 47% of the wells that are drilled find adequate water at a depth of 100 feet or less. A local man claims to be able to find water by dowsing, that is, using a forked stick to indicate where the well should be drilled. You check with 66 of his customers and find that 40 have wells less than 100 feet deep. Answer the questions below. Okay, we're going to assume the independence assumption is met. So our null hypothesis is that 47%. So the percentage of successful wells drilled by the dowser is equal to the same as what would be in the region. If he actually has skill though, then we would think that it would be bigger than 47%. All right, now it says assume the independence assumption is met, so we'll say it's satisfied. Randomization condition, you check 66 of his customers. That I'm not sure that they've said anything about randomization here, but those might be typical of his wells, right? 10%. 66 is probably no more than 10% of all of the wells in the region. Okay, I'll say that's satisfied. And 40 is bigger than 10, and 26, 66 minus 40 is bigger than 10. So this is definitely satisfied. So this one is definitely satisfied. We're assuming this one is, and I'm not sure what we might be able to take the fact that it's typical, but nope, they wanted not satisfied for randomization. All right, now we're going to perform the mechanics of the test. So here's what we're going to do. I need to move my calculator over, so give me just a second here. I'm just going to stop the share for a minute, and I'm just going to move the calculator out of the way because I can't do it with that thing there. Should have done it before, sorry. Okay, now I'm going to share my screen again. All right, there we go. All right, now, actually I want it over here, I think. Okay. So if I go to stat and over to tests, and we're going down to our 1 proportion Z test right here, option 5. The P naught we said is equal to 0.47. We got 40 out of 66. And we thought we were better than the P naught. So I want this option, the one that says greater than P naught. All right, so here's the results of the test. Notice it tells me my Z is 2.21, my p-value is 0.013, so 3 decimal places, 0.013. Explain carefully what the p-value means in this context. If his dowsing has the same success rate as standard drilling methods, the p-value is the probability of seeing results as good as those of the dowser, or better because of natural sampling variation. That sounds correct. Let's check the others. If his dowsing has a better success rate than standard drilling methods, the p-value is the probability. No, this is assuming the alternative is true. We want to assume the null is true. If his dowsing has a worse success rate, nope, that doesn't even make sense. What is your conclusion? Because this is less than 0.05, whoops, we reject the null hypothesis. And there is evidence to suggest that the dowser has a success rate higher than 47%. A philanthropic organization sent free mailing labels and greeting cards to a random sample of 100,000 potential donors on their mailing list and received 5,200 donations. They have had a contribution rate of 5% in past campaigns, but a staff member hopes the rate will be higher if they run this campaign as currently designed. Okay, what are our hypotheses? Well, they think they're going off of the standard rate of 5%. So my null should be P equals 0.05. All right, so it is in A and B, E, so we're looking at these three. All right. Now we're hoping it'll be better, so my alternative should be bigger than, which is this one right here. So we're going to choose option B. Are the assumptions and conditions for inference met? All right. So my success failure, at least 10. So this is bigger than 10. This minus that is bigger than 10. So this is met. Independence, there's no reason to believe that the donors are, because we're mailing this out, right? And it's random. So if I'm mailing this out to the donors, the independent assumption can be assumed to be met, right? And then our 10% condition, hopefully that sample of 100,000 is less than 10% of all donors. That would mean I need at least 1 million donors. I don't know whether that's true or not, but let's hope it is. Do you think the donation rate would rise? Okay, so let's look at what happened. So we're going to go stat, tests, 1 proportion z-test. Ours was 0.05. And we did 5,200. Out of 100,000. And we wanted bigger than the null. Our p-value is 0.0018. That's really small. That's less than a 1% chance of getting a response rate like we did by simple natural sampling variation if the response rate is really 5%. So the p-value is low enough to conclude that the rate would be above the previous camp. That's true. Okay, none of these other statements make sense, right? This is our statement right here. The P being low means that the result we got is weird if the null is true. Data from a recent year showed that 74% of the tens of thousands of applicants to a certain program were accepted. A company that trains applicants claimed that 215 of the 270 students it trained that year were accepted. Assume these trainees were representative of the population of applicants. Has the company demonstrated real improvement over the average? All right, so what are our hypotheses? All right, so we believe that 74%, so we should equal 74%. So that's C, B, or E. And a company that trains applicants claimed that 215 of the 270 it trained were accepted that year. So they think they're bigger than the 74%, so the B should be our hypothesis. right, so our 10% condition, 270 students is less than 10% of all students. That's probably true. Randomization is not true, but we're able to assume that they're representative of the population of applicants. And that's the purpose of the randomization. So I think they'll let us check that. If not, we'll come back and uncheck that one. Because they technically didn't randomize, but because they're representative, that's the point of the randomization. Success failure condition. So we got at least 10 successes, and 270 minus 215 is also bigger than 10. So those are both bigger than 10, that's fine. And then there's no reason to assume that they're not independent. So we should be okay there. Compute the test statistic. All right, let's do it. Stat tests 5. Our P is 0.74. We got 215 out of 270. And we wanted bigger than, so we're leaving it there. Calculate and whoops, I screwed up. Let me get that back. Okay, there we go. So my Z is 2.11. P-value is 0.0174. 0.0175. Would you recommend this company based on what you see here? Yes, the p-value is small, so they are hitting more than 74%. So the p-value provides strong evidence that the program is successful because it's very low. What? Oh, sorry. So they want some indication, not strong evidence. So that's pretty low. Their cutoff is the 1%, not. So a lot of times in the sciences, when we do less than 5%, we call that significant. Something between the 5 and 10% mark it can be moderately significant depending on the application. But they want that cutoff for strong to be less than 1%. All right. A magazine is considering the launch of an online edition. The magazine plans to go ahead only if it is convinced that more than 20% of current readers would subscribe. The magazine contacted a simple random sample of 400 subscribers, and 180 of those surveys expressed interest. What should the company do? Okay, so our first item, we need to check. Oops, I need to be able to draw. Okay, so we need to check the randomization. Well, notice that it says a simple random sample, so we're good there. We need to check their independent. So notice that it says we're doing current subscribers. There's no reason to believe that they're not independent, so we're good there. Now our 10% condition, 400 subscribers is less than 10% of all subscribers. That's probably true. And then success failure condition. This is bigger than 10. 400 minus this is bigger than 10, so we're met there. So yeah, all of our assumptions for inference are met. State the null and alternative hypotheses. So we need more than 20%. So our null is 20%, and the alternative needs to be bigger than 20%. Okay, so determine the test statistic. So now bear in mind what we're doing here is we're on, I need to be able to draw. We're on a normal distribution that's centered at the 0.2, the 20% for the null hypothesis. And we got 108 out of 400. So if I go over here and I say 108 out of 400, we get 0.27. So that 0.27 is right here. We want to know the probability of getting a sample that large or larger. And this is that value that we're getting back from the p-value. Okay, so that's what we're doing when we run this test. All right, so we go stat, tests, 5, 0.2, then 108 out of 400, and it's bigger than again, so that's correct. All right, so we got a z of 3.5 with a p-value of, now if this is scientific notation, what that means is 4 zeros. So I'd go I move it, the decimal over 4 places, so 3 zeros, and then 2327 is my p. Okay, that's how I read that significance. All right, so my z was 3.5. And my p to 4 decimals is 0.0002. That's that area right there. Since the p-value is low, we reject the null hypothesis. All right, so what should we do? If we reject, the survey results would be highly unusual if less than 20%. So we need to launch the online edition. An airline's public relations department says that the airline really loses passengers' luggage. It further claims that on those occasions when luggage is lost, 89% is recovered and delivered to its owner within 24 hours. A consumer group who surveyed a large number of air travelers found that only 6 of 125 people who lost their luggage on that airline were reunited with the missing items by the next day. Does this count cast doubt? Okay. So, we surveyed a large number of air travelers. That doesn't say anything about randomization. So I'm not sure that that condition is met. 6 out of 125, this is less than 10. So that condition is definitely not met, the success failure condition. So I can stop right there. No, they're not, those conditions. What? The independence assumption is plausible. Yep, I agree there. The 10% condition is met. I agree there because 125 is less than 10% of all passengers. But our success failure condition is not met. 6 is not bigger than 10. Now 125 minus 6 is bigger than 10, right? But the 6 is not bigger than 10. So no, the conditions are not met, but they want us to say yes. So the answer, say yes. All right, state the null and alternative hypotheses. Okay, so 89%, by the way, since the conditions are met, we shouldn't be doing the analysis, but All right, so state the null and alternative hypothesis. P equals 0.89. Okay, so casting doubt on the airline's claim would mean that we're claiming less than 89% is delivered. So my less than 89% is C. Determine this Z statistic. Okay. So again, 6 out of 125. 6 out of 125 is 0.048. So all right, so I should have done 125 minus 6 would be 119 out of 125. Okay, 0.952. So here's what we're doing. We're saying if the null hypothesis is true, then I'm on a normal curve centered at 0.89. We got a result of 0.952. So we want to know what's the probability of getting a result as weird or weirder than ours if the null hypothesis is true. This is bigger than. We said less than. All right, so in this case, I mean, you don't need a hypothesis. This question is just silly all around. I didn't realize how silly this was. I'll need to think about whether to include this on future homeworks. If my sample statistic is bigger than the population statistic, I don't need a hypothesis test to tell me, right? Because we should not be shading this area. We should be shading the less than, right? That's what the hypothesis says set up as. So this is just screwy, but let's go ahead and run the test. So we're going to go to stat, tests, 5. My P is 0.89. My X is 119 out of 125. Oh, I'm sorry, I misread it. 6 out of 125 met the condition. Oops, oopsie, oopsie, oopsie. So let me erase. Where's my eraser? You shouldn't be using the 0.952. All right, well, let's just clear the whole thing. All right, so now because I misread it, it now makes a lot more sense, right? So trying to get my thing to draw here, right? Got a normal curve centered at the 0.89. Our result should be the 6 out of 125, which is the 0.04 or whatever it was, 0.045 or something like that. And we're shading this way for the p-value. So yeah, it's going to be really unusual. So it's going to be, so let's go back over to our calculator. And go up. This should be the 6 out of 125. And we wanted the less than, so we're going to choose that condition. Calculate. And there's our Z, right? So our Z is negative 30.09. P-value. To 4 decimal places, it would still be a 0. Now, we never actually say the probability of something is 0 because there are very few events in life that have a probability of 0. The probability that tomorrow I'm going to wake up a man is 0, right? That would be something with a 0 probability. But barring an impossible event, what's the possibility I could wake up tomorrow a millionaire? Well, it's not very likely that that's going to happen, but who knows? Maybe I have a great aunt 5 times removed who suddenly died and left me $1 million, and I'm going to wake up tomorrow and be a millionaire. It's not a probability of 0. The probability is so small, it might as well be 0, but we never actually say a probability of 0. So when you get back a really small probability like that, what we usually do is just say the P is less than 0.01, and that indicates a less than 1% chance. It's a really small probability. All right, but this software doesn't allow you to do it, so let's put in the 0. Do the results of the survey cast doubts on the airline's claim? Yes, because we would reject the null hypothesis with a probability that low. All right, guys, this gets you through the homework. If you have any questions on the Chapter 19 homework, be sure to let me know.